sort of um, a panoramic view of optimal control starting from calculus of variation. So if you look at my talk, as you see, I start with defining what is an optimal control system, then straightforward optimization problems, then how we went to calculus of variations, then coming back to what is it that we have as an objective in a control system, and then the Pontryagin maximum principle, and how the proof of that is different from what you would normally encounter before that time. So let's proceed. So this is let me acknowledge these people. All my material for this talk has been taken from this book, Calculus of Variations and Optimal Control. This material was very nicely assembled by one of my recent dual degree master's students, Anant Joshi, who's now at Illinois doing a PhD. I'm also indebted to many people who taught me optimal control very well. There were many notions which I was not clear about. I was on shaky foundations. In particular, I thank colleagues Debashish Chatterjee, Mishal and my former graduate student, Mishal Asif, and another colleague from Caltech days, Dongyi Chang, all of whom made me understand this theory better. So let's start with what is the notion of an control system and then an optimal control. So we guys who do control systems either deal with continuous time control systems or discrete time control systems. Almost all implementation is done in this form. All right. So in discrete time control systems, more often than not, we are looking at ordinary differential equations governed in time with some states and some external inputs, which we call control. What is important is that this set of control inputs, they at every instant of time belong to some subset of Rn. And in addition to that, we could also impose things like continuity with respect to time, differentiability with respect to time, and so forth. Now, the same thing goes for discrete control systems. The key difference being now we have algebraic difference equations, right? All right. So this is, and what is, okay, when you look at this, you wish to synthesize this control. Now you wish to now synthesize this control to meet an objective, at the same time minimizing or optimizing a performance measure. So here is that performance measure. So it has a component based on the final time and the final cost, assuming we are going from T naught to TF, right? So T naught is the initial time, TF is the terminal time, and then there is a running component of the cost, which is dependent on time, the states, and the control, right? So these are explained here. Now in the discrete time, if one looks at it, so you have the discrete time cost. So our objective as optimal control synthesis engineers is to come up with a control history. That is that control which minimizes this and achieves some objective, right? So you have a cost function which you wish to minimize. So for instance, you could achieve objectives using many controls, but what is the control which minimizes such a cost function? So now let's go on. So before we start with control systems, so let's go back in time. Let's recall something as plain vanilla, straightforward optimization. So you have a smooth function, let's say from a single variable of in the real numbers of f of x, and you want to find out what is the minimum of this function f. So what was what were the necessary or essential mathematical tools that you used from calculus was the first derivative at the candidate optimal control is 0. And if it has a minimum, it has a local minimum, then the second derivative is positive. So this is a sufficient condition. For instance, if you had got f double prime x star is also equal to 0, then you have to go to higher order derivative. So now instead of just R, you made this from n real variables, then you would have extensions of this form of the gradient, and this second order condition would come out in the form of a Hessian. So you insist on the positive definiteness of this Hessian. So this is straightforward vanilla optimization, right? So I thought I'd explain it, but I think that's straightforward. I don't need to go into it. So now here is the key feature when you do this, which translates to when you go to more involved optimization or optimal control problems. So you were looking at some domain in Rn in which you wish to minimize this function. Now, what do we mean by the notion of a local minimum? Let's make that clear. X star belonging to this domain, right, is a local minimum of f over d if there exists an epsilon greater than 0, epsilon being a non-negative real number, such that for all x in d and for this condition being satisfied, fx star is less than equal to f of x. So what does this mean? So let me go back here. So you're claiming x star is some minimum. So here is your Rn, and you're looking at this problem in some domain D, right? And you're claiming f at x star is a minimum. So then you want to get some domain around x star in which the following condition will hold. This condition holds. Only then can you call this a local minimum. Why is it a local minimum? Is because this condition is in a local region, right? This is a local region, and therefore you call it a local minimum. Okay, now this is plain vanilla optimization, whether in n real variables or one real variable and in a domain, which is you get a local minimum. So this is not answering a question. Suppose you had a function of a real variable. So let's say x, and you had something like this. So this may be a global minimum. So if you look at this entire part as your domain, but what you're getting answers here is points like these, which are local minimum or local minima, right? So you would have similar notions if you want to talk of global minimum or the minimum in a domain. So you would have to search over all such local minima. Now, I don't need to go over this conditions for unconstrained finite dimensional optimality. This is straightforward once again. Now let's come to constrained finite dimensional optimization. So these are optimization problems as before, right? But subject to these constraints. So I'm sorry, this was a LaTeX typo. So you have M constraints. See, remember, you have an optimization problem in n variables, and now you have M constraints. So what's meant by that? So you have to satisfy h in xn equals 0, and so on. You have M such constraints, right? So this is what this is saying here. Now, we also assume that the constraints are linearly independent in the domain you're considering. So what does linearly independent mean? That the m rows of the gradient of h. So each of these functions, you can have nabla h1, which is like dou h1 by dou x1, dou h1 by dou x2, etc. So this is an 1 by n vector. Like this you can have for each of these, right? So this becomes an M by N matrix, and this should have rank M at every point in the domain that you're looking at. So that's what is meant by linear independence. Then you have a result which brings in for the first time your notion of a Lagrange multiplier, right? So the necessary condition now, as opposed to before, is that there exists m such scalar lambda 1 through lambda m star such that this is equal to 0, right? And for and the second order condition, which is with respect to, just like earlier you had the second derivative, now you're looking at the Hessian in some sense, right? Of this is greater than equal to 0 for all d which satisfy this condition. I'm not going into specifics of this, but this is in constrained finite dimensional optimization is where you bring in the notion of a Lagrange multiplier. Okay, so now comes, okay, now let's see. Now, so far, everything was the calculus that we had learned. Now we come to problems where the questions asked are sort of more tricky. For instance, let's look at a mechanical system. Let's say it starts at some configuration Q naught. So I will, when I say Q, it belongs to what is called Q of a mechanical system. If you want to think of a simple pendulum, think of this as it starts from a certain angle and goes to another angle, right? So now I would like to answer the question, if a mechanical system starts from point Q naught and wishes to go to point Q1, there are many ways it can go. It can travel from Q naught to Q1, right? Now, which is the path which minimizes, to be more precise, makes it stationary? So we cannot right away claim it's a minimum of something called an action functional. So let's not worry about the action functional. Let's think of it as a cost, right? So which amongst these trajectories, which, so this is like asking a question now in a different setting. See, earlier when you did straightforward plain vanilla optimization, you looked, you had some function of x, and then you claimed this x star was the minimum. So you you went close by to these points and found that at all those points fx was greater than fx star, right? So now the question we are asking here is, which of these curves, now instead of looking at points, look at curves now. Which of these curves will the mechanical system take in order to achieve a stationary point of something called an action functional? And that's where that comes from your notion of a Lagrangian in mechanical systems, from your kinetic minus the potential energy. So now, before we start with all that, because we are now dealing with curves, right? We are dealing with curves, say from an interval AB going to Rn. Now, what does this signify? How many times is this curve going to be differentiable? What are you going to insist? To start with, if I say C1, is it once differentiable? C2 means twice differentiable. What is the class? So I have to begin with, lay down this set very clearly. What is the admissible set in which I am posing my optimization problem? So one is this set, and the other thing is, remember in the plain vanilla optimization, if you recall, when I was looking at points close to some x star, I assumed some norm condition, right? X minus x star in some region less than epsilon. Now, what will this translate to in terms of an entity like this? When you're talking of curves, you're not talking of single isolated points. So therefore, we need to define a notion of a norm associated with these functions. So this is a zero norm, this is a one norm, and this is a p norm, right? Now, look at how the optimization problem has evolved, and it has got made itself start from the original simple steps of optimization. Now, from points, it's gone to curves, curves with a certain degree of differentiability, right? Then we want to define notions of proximity. Therefore, we have started defining norms. Now, if you wish to, now if you talk of a cost function, which is a function of this curve, now y is a curve. Earlier when I said j of x, x was a point in Rn, right? Now let V be a function space and A be a subset of V. This functional, that is which takes A to R, we call y star a local minimum of j over A if there exists an epsilon greater than 0 such that for all y in A, this is satisfied. Look at how closely this definition sort of um, follows or goes in parallel with the earlier one on finite dimensional optimization. It's just that you have to get in the proper tools of talking about such inequalities. So like the distance of another curve to this curve, the notion of the functional over this set of curves, etc. All right. Okay. So now, earlier when you looked at things, you said DF, remember, when it's straightforward, plain vanilla optimization, at the candidate point, you said equal to 0. Now, what does that translate to in the case of curves? And when you're talking of comparing curves and optimization criteria which depend on curves, so you bring in this notion of a variation. So you have the notion of a variation which is called a, which is a linear functional going from this admissible set of curves to a real number. Now, a linear functional is called the first variation of J. Remember, J is the performance measure at some Y. So let's maybe I'll get a page and mm, okay. So let's say we have an optimization problem, which is a curve from here to here, right? Now, at this point, I would wish to define, right, at so this entire thing is the curve I'm talking about, right? This whole thing y. Now I want to define delta j at y. So this is like in your earlier case, you had talked of df by dx in the finite dimensional optimization at x star. Now we call it delta j. So there f was like the measure of performance. Here j is the measure of performance. And this is taken at the candidate curve y. Now a linear functional is the first variation. So think of this as your d by dx, the first derivative of j at y. If for all alpha in the real numbers and eta in y, this, right, this quantity, so this is like a Taylor series expansion in alpha, alpha being a scalar, right? So you have the first functional alpha and then the higher order terms. This would be called the first variation. So jy plus alpha minus jy divided by alpha. Note that these are real quantities and the limit as alpha tends to 0. Now, let me not dwell on the second variation, etc. But the idea of this is just as you had infinite dimensions, with the proper mathematical tools, you can extend it with the notions of variations. So this is variational calculus. Now, the conditions for optimality also look very similar. They look this way, where these are admissible perturbations which come from the same class of curves. This is one thing important to bear in mind here, that remember when you say jy plus alpha eta, this alpha is a real number, but this eta comes from the class of curves where y belongs. Y also belongs to a class of curves. Like I said, it could be once differentiable, twice differentiable, and so on. Right? So you have a condition like this for all admissible perturbations eta in V, right? Okay. Now, this was the technique used by many mathematicians and physicists for a long time. I mean, you can sort of read about these problems right from this 18th century, or maybe, yeah, 18th century, 19th century mathematical expositions on these problems. So let's give some example. So here, you want to maximize the area under a continuous curve of fixed length with fixed endpoints. So what is this? So you have fixed endpoints, right? And you have a curve of some length L, and you wish to maximize this area the way you choose. So you want to choose this curve. So basically you want to decide what f should be f of x, or y equals f of x, right? You've been given a, b, and so this is what you would like to maximize. So y of x dx, so this is like you're taking elemental areas. So this is, if this was x, y of x dx, right? Now, subject to, this is subject to a constraint. That's the length constraint. That's the length constraint. And then you go about solving this problem using the type of conditions that I have just now explained. So this is another very classic problem here. I will just show you this slide for a short time. And then this is the shape of a string of fixed length suspended at fixed endpoints. But I'll come to the most classic problem. You will have a copy of these slides, so you can take a look at this, is the Brachistochrone problem. What was the Brachistochrone problem? Let me go to the next page. So you had 2 points, A and B. So gravity is in this direction, right? So they are laterally displaced as well as vertically down. So what is the curve? Say I have different curves from this point, right? What is the curve under which, if I leave a point mass at A, will it reach B in the minimum time? This was called the Brachistochrone problem, and apparently it was solved by Isaac Newton for the first time. And here I have described that problem in terms of all the parameters. So please take a look at that when you look at your slides. So now let me move forward. So now, so far, I have not brought in the word control. I have spoken about initially straightforward optimization. Then I spoke about optimization over curves of certain cost functions or functionals, but I have never brought in the word control. Now I will bring in the word control in the following form. That is, if you have to minimize something about a curve y function of x, this y prime often can be looked at as the control in the problem. Now, there are a few other things here which I will not go through. Weak extrema, strong extrema as of now. They are, to give you a quick example, suppose they are important because suppose I were to sketch, let's say I have a curve like this. Then I'm given two other curves. This is another curve. Then I'm given one more curve, which probably looks like this, right? Now, if you see, if you just took a norm, so let's call this y2 and let's call this purple one y naught and the red one as y1, y1, right? Now, if you ask the question, is y naught close to y1 or y2? It depends on the type of norm you choose. For example, if the norm was just the distance norm at each point, at each x that you chose, then you can say that y1 and y naught are close to each other. But if the minute you added something like a derivative component, then the jittery part of y1 comes into place, and that would be far more away distance wise in the norm sense than y2. So this notion of a norm is very important, but let's not get into that. Now, related to this comes a very important set of equations, which is called the Euler-Lagrange equations. So I'll just go through this. So please remember, you will have a cost function of this sort. And since Euler-Lagrange brings in the notion of mechanics, so think of, so in mechanics, if I were to write that L, I would write it as a function of time. And if you have all the coordinates Q, Q is a function of time and Q dot. And this, as many of you know, is the Lagrangian, which is T minus V. And then you integrate this over an initial time to a final time. So that is your Lagrangian. And now let's go through these steps. So we want necessary conditions. Let's not get too worried about strong extremum for an extremum. So you have permissible perturbations, right? And such that y plus alpha eta lies in the original vector space. Remember, eta, the perturbation has to be from the same vector space. Then we look at conditions such that this, this should be equal to 0. That's missed out here for all admissible eta. And from this type of calculation or derivation, you arrive at a set of equations of this form, which are called the Euler-Lagrange equation. Okay, so we started with this class of curves, and for the time being, I've told you to look at this as the control, but you don't need to do it right now. Right now, we are just looking at curves and optimizing over curves, but with a certain cost function, which is here. And I have related this cost function in the case of mechanics to something in time. Here I've got x, q, and q dot. And this leads to your Euler-Lagrange equations. Now, many of you may have heard of something like the Hamiltonian formulation of equations in mechanics. That's just a change of coordinates that you define a new variable in terms of the partial derivative of the Lagrangian with respect to y prime, right? And then call a Hamiltonian, which has the p embedded. So if you rewrote the Euler-Lagrange equations in terms of this Hamiltonian, you get this set of equations. So that's the Hamiltonian formulation. So now, for the first time, let me bring control. So far, it's been calculus of variations and curves and how do we choose curves. But now this is now going to be straightforward. So let's get back to our first problem. Ordinary differential equations, some initial conditions, then some assumptions on what f is, also partial of fx. These are required for certain mathematical assumptions we make along the way, or sort of mathematical conclusions we make along the way. And now u is a piecewise continuous function of time. So the same, this is almost the same: cost functional, running cost, terminal cost, initial and final time. Okay, so now in an optimal control problem, you could have different target sets. So the final time and state, remember, we are talking, for those of you not familiar, so we are talking of a dynamic model with time, states, and control, right? I'm sorry, this is a typo here, so it should be this. Okay, so you could have the final time and state not specified, which is a situation like this. Final time is not specified, but the final state is specified. So I'm sorry, this should be XF. Final time is specified, but final state is free, right? Final state is free. So now here is where in control there is a subtle difference. See, earlier when you were talking of the running cost function of x, y, and y prime, you were talking of working on curves. But now in control, if you are perturbing the control, and that control enters your equation like this, right? Now, therefore, you have to perturb the controls in the class of admissible control, and this in turn perturbs the state. The control now perturbs the state, and then you go about going about the same way. All your first order necessary conditions. Now this is this eta. Now you will see the eta, but the eta is the perturbation in the state. See, use a different color. Psi was the perturbation in your control, and eta is the corresponding perturbation in the state. And then you get a set of conditions in terms of differential equations. I'm not going to run through all this, right? But the way you go about is the same, the way you take variations, etc. And you can look at the problem in terms of an Hamiltonian. So these, I have included these derivations so that later on when you look at the slides, you can get to know that these are just mathematical sort of exercises which are making use of the same notions of variational calculus. Okay, so then, right, indeed. So once you're done, remember I told you you could reframe things in terms of a Hamiltonian, right? You get the equivalent of your Euler-Lagrange conditions, but now in terms of these. And where does your control come? It has a maximum at every point along the Hamiltonian. The Hamiltonian gets maximized by the optimal control. And these are your final equations. So these are first order necessary conditions for an optimal control law. Okay, so here is where now I will make a departure. Now let me give you a chronological perspective so far. All that I have spoken about so far is material which was done till 1950. So it was then, I think, I don't remember exactly when Pontryagin wrote his paper, and I think 1951, maybe So the big contribution of the Pontryagin maximum principle was that it just broke away from all these calculus of variation techniques. So it considered newer class of inputs. For example, in some of these techniques, suppose I have an on-off type of controller, or a controller in which, let's say, I'm torquing a robotic arm. I suddenly apply 1 Newton meter clockwise direction, and then -1 Newton meter. So this is anti-clockwise direction. The theory of calculus of variations, because of its assumptions on continuity and differentiability, etc., could not address problems of this nature. So it was there that Pontryagin contribution was very valuable. And his whole approach to this theory of optimal control was from a geometric perspective. Well, not that what we have discussed is not geometric, but geometric from a sense that it it sort of rested on the sets, on the notion of separation of convex sets, so that you can have something called a hyperplane which separates convex sets. So now let's move on to Pontryagin maximum principle. So again, optimal control formulation. I'm sort of repeating this so that you have, you sort of, it stays with you. This is there. So again, target sets. So repeat of what? Okay. So now in his paper, he looks at two problems: fixed endpoint problem and a variable endpoint problem. So I call this P1 and P2. So let's not worry about this right now. We could probably come back later, and I won't even state the maximum principle, but what I would like you to first have a feel of is the flavor with which he approached this problem. So it's a set of 4 authors. The Pontryagin paper is Pontryagin, Gamkrelidze, Boltiansky, and one more person. I'm sorry, I forget the name, but I can provide that reference for you. So what did he do? He augmented the state space with the cost. So this is the original state, and lying above is your cost, your running cost, and this was your augmented system dynamics from your. So we have now moved from, so I've not shown you the slide. This is the final theorem. I'll come back to it later. So yes, from this, he augmented the state by one more quantity, was which was basically dependent on this, right? So this is the way he did it, right? Okay, so now y has x naught and x, right? Now let's look at this figure. So on the vertical axis, I've plotted x naught, the running cost, and the rest of the states are here. So now when I start out, the cost is 0, right? I start at some initial point x naught. Now at some given point of time, or let's say I'm at some, okay, I'm at some state x1, I may be here. So I have some value of my cost. Now I put this as 0 because if I project it down, this is 0, right? So I may be here. So first and foremost, so this is a notion of the augmented state space and the augmented cost. So what did Pontryagin do? He said, let's consider, don't look at the math here, two types of control perturbations. That is, suppose you said U was an optimal control for this problem. Now, what did I do from my original approaches in calculus of variations or finite dimensional optimizations? I perturb things a little bit to see what happens to the cost, right? That's what we were doing. So now he said, let's look at temporal control perturbations. What do they mean? So let's say this is my control, and suppose it stops at time t star. Now, let me think of a perturbed control. The control acts for some more time. So it acts for some more time. Alternatively, if my control acted up to t star, it could act for lesser time. So here it stops here, the control. So these are temporal, time related perturbations of the control. So in this case, it's positive time. In this case, it's negative time. All right. So now, then apart from temporal control perturbations, so see, look at the very large class of perturbations he considers by this. One is just temporal. The other, he said, was called spatial control perturbations, which he called them needle perturbations, right? So there again, this math, please look at it after you get the basic idea. Then it becomes all clear. It's just first order calculus, Taylor series, nothing more than that. Nothing to be scared about. Then he looked at spatial control. So now let's look at this. So you have, say, from T naught to T star, initial to final time. Suppose you decided this was the optimal control. He said, let's look at perturbations of this form. Suppose this optimal control at this point, I perturb it. It has a jump. It jumps to some W value. And then, so he allowed perturbations of this type in his control. These are called needle perturbations. So this W lasts for some time interval epsilon A here. For some time interval it lasts, and then you're back to your original candidate optimal control. So he considered these two types of control. Now, apart from this, I said he sort of broke loose from the earlier calculus of variations approach. So far, there's no variational calculus. He's considering spatial control perturbations, temporal control perturbations. Now, this here is the augmented state. See, initially with the optimal candidate optimal control, now you perturb the control, you have some other trajectory, right? Okay. So then, let me not, even before I come to this, let me uh, go through. I think I should have changed the order of this, but let me, okay, I'll first, yeah. So now when you perturb controls, so you can reach other points at a given time, right? So for instance, um, if you have reached a certain point with a certain cost, and now you took a perturbed control and this reaches the same point with a higher cost, then obviously that perturbed control is not going to work. But now you must find a way of separating those points which give you a higher cost from those points which may lead to a lower cost, or rather those perturbations which may lead to a lower cost. So this is what he did. Okay, let's look at this figure first and then go back to things. So what is this figure saying? So if you look at this, I have a quantity called Cp star. The reason I call it C, it's the convex cone. So let me, maybe the notion of a cone. Okay, so what is a cone? A cone at the origin. So let me take this as Rn. So a cone at the origin. Let me use a different color. Is a set of this form K, which K is all, so it satisfies the following condition that, sorry, if x belongs to K, it implies alpha x belongs to K for alpha greater than equal to 0. So a set which satisfies this is a cone at the origin, right? So now over that, you have a notion of convex cones. So convexity is a property. So let me just describe that as well. So this is a cone. Convexity is a property. So if S is a subset in Rn, so I would say S is convex if for any 2 points x1, x2 in S, alpha x1 plus 1 minus alpha x2 is in S for all alpha less than. So this is the notion of a convex set in Rn. This is the notion of a cone. And if a cone is also convex, it's called a convex cone. So coming to Pontryagin idea, so he showed, or rather he worked on computing the set of all states. So here is that set which could be reached by perturbed controls, both spatial and temporal perturbations, control perturbations, and these he showed formed a convex cone, right? And you could, so this was the augmented state at D star, and this direction here is a direction of decreasing cost. So what is this showing you right now? It is showing you inside this, which I ask you to accept as a convex cone, is all points that can be reached by a perturbation of the control. And the other thing, just give me a second. I'm sorry. Yes, the other part is as is a direction which leads in the direction of decreasing cost. So now let's get to the theorem, which is the crux of the Pontryagin principle. If C and D are two non-empty disjoint convex sets, so in this case, CT star and mu. So you let's think of CT star, and this is my, so you may wonder what this, okay, let's erase this and let's maybe use a different color. So this is the other set. So this is set 1, this is set 2. Both are convex sets, and therefore now you have a separating hyperplane between these two sets. This is just like an arrow in the negative cost direction. The state remains the same. It's just it look like this. So if you look at the slides, you will figure it out. And this is all these states that can be reached by a perturbation of the control. So now, if C and D are two non-empty disjoint convex sets, there exists a hyperplane that separates them. So here is that hyperplane I'm talking, and in this case, this is the hyperplane, right? Now, for those of you who have encountered Pontryagin maximum principle in some sense and have seen things like Lagrange multipliers or the co-state equation, those co-state or adjoint variables are precisely this. And it is the propagation of these variables. So what is this? This is So you describe a hyperplane by a normal to the hyperplane, right? And this is that normal vector. So let me delete part of this so I can write things now more clearly, I think. So, so now this is the normal vector normal to the hyperplane, which is given by this. And what you may have seen as adjoint equations is the progress or the evolution of these vectors. That's what forms the adjoint equation. So the whole idea is based, Pontryagin maximum principle is based on, this is the crux of the maximum principle, that C and D are two non-empty disjoint convex sets. There exists a hyperplane that separates them, right? So now let's look at some of these conditions. We probably, so let P naught star PT, P star T star, as I've shown you here, denote the normal to the hyperplane that separates mu, the two convex sets, mu and CT star, mu and CT star. Look at these figures, right? Then I can say the following. What does this mean? That is gamma plus Y star T star is in CT star. So what does that mean? So if I have a vector here in this, it will obviously make an obtuse angle with the P naught star P star vector, and therefore it makes an obtuse angle. The inner product will be, let me use a different color. The inner product should be less than equal to 0, right? In the same way, this vector with the mu, because the mu is in the same direction, is in the same half plane, what is below this plane, right? Therefore, that would be an acute angle. Therefore, this would make the inner product would be greater than equal to 0, right? So this is the crux of the Pontryagin maximum principle. And I think I'm at 52 minutes. So Mangal, can I take about 5 to 10 minutes more? Would that be
Yeah,
fine?
yeah, it would be perfectly fine.
Okay. All right. So once you have these, so now let me take you back. I hope I have not confused you significantly, but I think what is to be appreciated is the fact that the PMP breaks away from all the earlier tools that were used in optimization and optimal control. That should be understood by you, and that it depends on this very beautiful notion of separation of convex sets using a hyperplane. Uh, right? And the adjoint equation that you see is the propagation of that hyperplane. So now let's read some of these slides, which now become clearer. I said direction of decreasing cost. So the rest of the state remains the same, but this is a direction of decreasing cost, -1 vector, right? Since U star is optimal, this should be directed outside of, else the cost would decrease, right? Now, so what does this mean intuitively? If Y star T star plus mu is directed into CT star, then there exists a perturbed trajectory that is based on a perturbed control which has a lower value of the cost function than the optimal trajectory. However, we are saying U star is optimal, so this is not possible. So this is the intuition. Okay, and the rest of this is so convexity theory. All right. So now let me, so I wanted to give you the geometric idea. Now here is where you incorporate all your perturbations. So these are your temporal perturbations. These are your spatial perturbations. These are your temporal. So because you could have many temporal perturbations, right? You could have many spatial perturbations. Along the way, you have maybe m such perturbations, right? And this was your original point that you had reached, and to that you added all these points. right? Now, I think I will not maybe tell you more. Now let's read the main theorem, Pontryagin maximum principle. You could go through all of this, and I guarantee that you'll be able to work out things. Look at Daniel Leberzon's text, beautiful textbook, written extremely well, and you will follow things. So now here is the main maximum principle for the free final time and final state condition. So let's now go through it and we will conclude our talk. Let U star in this time interval be an optimal control and X star be the corresponding state trajectory. So star means optimal, right? Then there exists P star from which is a mapping from the reals to Rn. This is your adjoint and the constant P naught C. See, if you've done optimal control, they talk of this as the abnormal multiplier, right? Now, there is a reason why it's less than equal to zero. I've not had time to show you that, but that's also very easily understood if you understood that one figure I showed you of the separation of CP star and mu. You will easily derive it, and the slides have the derivation as well, right? Now, this is a very important point, that this augmented vector in Rn plus 1, because this is Rn, this is real, is never zero, is never zero on the entire time interval. This is an extremely important point, because if it becomes zero at any time on the time interval, then it will remain zero. So then you have the following properties. So you have the state evolution, the adjoint evolution, where the Hamiltonian is defined this way, again on the same lines as you had seen before. And at every time t, the Hamiltonian is on the optimal control trajectory. And you use the optimal control as opposed to using any other control from the set of permissible controls is always maximized, right? And for you can also show that for such fixed, this 1 minute, I wrote fixed, and this was the fixed endpoint problem. Sorry, yes, fixed endpoint final time is not specified. Okay, that the Hamiltonian, the optimal value of the Hamiltonian is 0. So there are variations to this, but you can pick it up very easily. What is important is to understand this beautiful idea of Pontryagin, where he talked of the whole um, optimality in terms of separation of convexes. I think I'm almost done. I hope I've gave you a good overview of things. There are lots of details in the slides. Please take a look at these. And yeah, I have, for instance, not emphasized all this, but you could take a look at this based on, this is all first order variational calculus, nothing more than that. And again, the adjoint dynamics comes in here. And the way we get all those conditions, the Hamiltonian maximization, I have sort of emphasized this here. Okay, Mangal, I think I will stop here and I'll happily take any questions.